This presentation is delivered by the Stanford Center for Professional Development.
I have a one handout for you today. I expected to have two, but we had photocopier drama this morning, so I haven't photocopied your assignment yet. I'll post it as a handout after class today. You have plenty of time to do that. I'm not going to make this due until 2 Mondays from now, so it's not like you're in an immediate rush to get started on it. So that's why I wasn't stressing about it. But nonetheless, the assignment will formally go out today, and you'll have 2 weekends to do it. It's actually not too bad. It certainly involves some of the new threading stuff. You're revisiting assignment 4. You're implanting some thread directives to make a lot of stuff that was running sequentially before, and you felt the pain of that sequential execution before. Make it so that lots of things run in parallel, and things run really, really quickly, really, really beautifully. It's very impressive. It's a good end result once you actually get that thing up and coded. When I left you on Wednesday, you were all stressed because you had a midterm in 7 hours. But I was just getting through the dining philosopher's example. Let me review the picture. The idea is that there is food, big plate of spaghetti, at the center of a table, and there are, I'll be less caricature about it this time, there are 4 philosophers, and I'll put P0 there, sitting in a circle, and there are actually what look like pitchforks, but just regular forks, in between each of them. And each of those philosophers is designed to run in his own thread, and they follow the recipe that is, they think, they eat, they think, they eat, they think, they eat, and then they think again, and then they exit as a thread. That is their day. In fact, that's in their entire life, because they only live for one day. Okay? So I set this up as a global resource, because that's the way the handout deals with it. I will emphasize again that the way I'm writing this is shorthand. All I'm really saying here is this is a gesture to the fact that I have 5 global semaphores in an array of length 5 that are all initialized to 1. There really are some semaphore new calls that are involved to build that thing up, but I don't want to focus on that other than just mentioning it. Each one of those ones basically represents the availability of a resource. If I call this fork 0, and this is fork 1, and fork 2, and fork 3, and fork 4, when this particular semaphore is locked up in this synchronized manner at a 1, I know that this particular fork is available. And that is of interest to philosopher 1 and philosopher 2, because both of those have to contend for that fork in order to pass into the eating phase of the thread. Okay? So without concerning ourselves with the deadlock scenario that was outlined last time, this is basically the thread I want them to follow. Each philosopher knows their subscript or their ID number, and that influences which forks they grab, or they try to grab. And so, if, where did if come from? For int I is equal to 0, I less than 3, I plus plus, I want each philosopher to grab fork to the right, fork to the left. That grabbing happens via 2 semaphore wait calls against forks of ID. I messed that up last time, I wrote I. Forks of ID, and then forks of ID plus 1, but we want to mod it by 5, just so it wraps around. And let's, there we go. There. Okay, and as long as they pass through those and return from those 2 semaphore wait calls in sequence, they're allowed to eat. This is after they think for a while. Okay. After that happens, after they eat for a while, they semaphore signal these things. I don't really care about the order in which they free them. It doesn't really impact execution in any interesting way. Forks of ID plus 1 mod 5, and that is more or less what they do. There's an isolated think after the last meal, and then they return. And I did my little choreography last time where, in principle, because each of these 5 threads may be running in round-robin fashion, they probably will be, each one might get to the point where they grab the right fork. They're enough through this call that they've effectively acquired the fork because the 1 has gone down to the 0, but they get swapped out sometime between the actual demotion there and the time they actually demote the 1 to a 0 inside. Does that make sense? So it's possible. I don't want to say it's unlikely. It's actually it's actually unlikely unless you force it to happen. But actually, I don't want to say that. Because it's possible, it's a problem. If all 5 threads could be swapped out right here and all be experiencing mutual deadlock because they're all depending on the philosopher to his or her left to be releasing the fork that is their right but your left fork. Okay? Does that make sense? Normally what you do, put all your semicolons in, but normally what you do is you implant the minimum amount of work to remove the possibility of deadlock. We made some observations in the final 10 minutes of lecture on Monday, or Wednesday rather, where we know because of 5 div 2 is 2, that at most 4 forks can be held while philosophers are eating. Okay, so we could recognize that there are at most 2 philosophers going to be able to eat at any one time. So we could actually put something of a generalized counter right there and right there, and actually force each philosopher to become one of the blessed 2 that's allowed to go ahead and grab forks. Does that make sense to people? Okay. So what I did is I did this semaphore, a single semaphore, num allowed to eat, and I could initialize it to 2. Let me get rid of these arrows. And I could sneak in a call right here where I say, please wait for me to be one of the 2 that is allowed to eat. Okay? It's something of a critical region. It's not the same type of critical region we saw before. Critical region normally means at most 1 because there are concurrency, there are race condition possibilities. This is a different type of critical region. In fact, most people wouldn't call it a critical region, but I'll call it that. But we only want 2 threads to be somewhere between here and this part right here. Okay? Because if we have any more than that, then we're nearing the scenario where we might have deadlock. Okay? Does that make sense to people? So let them go ahead, grab forks, eat, release the 2 forks, and when they're done, saying basically I have left the table. So that means I should signal all the other threads or all the other philosophers that might be waiting for permission to grab forks and do a final semaphore signal call right there. Okay? Does that make sense? Now, if you put 2 there, I would completely understand why you did that. I personally, even though I recognize that there are at most 2 threads allowed to be in here, okay, or the way we've actually programmed it up, that at most 2 philosophers will really be calling the eat function. My preference, just because I'm a purist about it, is that this be a 4 instead. Okay, now a really terrible value would be 5. If I have 5 philosophers, then basically the semaphore wait is just this gratuitous semaphore that everyone has to consume, but there will always be 1 there. The reason the 4 works is because as long as somebody's prevented from grabbing either fork, then there's at least 1 philosopher thread that's capable of grabbing 2 forks. Maybe the other 3 are blocked, okay, but it's always the case that at least 1 philosopher will be able to grab 2 forks. That makes sense to people? That's the minimum amount of of a fix that I need to implant into the code to make sure I don't have deadlock. So concurrency and multi-threading purists usually like to do the minimum amount of work to prevent deadlock. There's a reason for that, because the minimum amount that you implant there, you remove the deadlock, but you still grant the thread manager as much flexibility in how they schedule threads as possible. Okay? When I put a 2 there, I'm taking more control over how threads are scheduled. That means up to 3 threads can block on this line right here as opposed to just 1. Does that make sense? Okay. If you make this a 4, that means that up to 4 threads can make as much progress as is really possible before they're blocked and pulled off the processor. Whereas if I make it a 2, we're blunting some threads prematurely. Okay. Does that make sense? Okay. So that's what I like about that, and this is why I prefer the 4. If you put 2, 3, or 4 there, it will be programmatically correct. If you put 2 or 4 there, I think it'd be correct from a design standpoint. I prefer the 4. Yep.
Maybe this is a dumb question, but why would we use a semaphore as opposed to like an if statement on like a global variable? Is there any really good reason to?
We could. In fact, I'm going to talk about that specifically. You could, rather than doing this, where you actually have the integer. Basically, this tracks a resource. I like to think of this as the number of shopping carts that are available in front of Safeway. Okay, and if there are 5 people that approach the store and it's a requirement that all of them have a shopping cart, they all flash mob the 4 shopping carts, but only 4 walk away with 1. So 1 is blocked until at least 1 shopping cart comes out the exit door. Does that make sense? I could, and I think this is actually a really good question, so pay attention to my beautiful answer here, that I could have just put a global integer here and set it equal to 4. I could have had this check to see whether or not it was greater than 0, and if so, acted on it. But then I have the separation between test and action that was problematic in the ticket agents example. Does that make sense? Well, you could solve that by having an exposed global integer and a binary lock like we did for the ticket agents example. But then what happens, and you have to think about this, I don't really want to write any code because I don't think I have to. Rather than just blocking on the semaphore and letting the thread manager decide when you can get the processor back, what you'd have to do is you'd have to do some little while loop, okay, around and repeatedly check to see whether or not the global variable went positive from 0 if you were blocked on it. Does that make sense? You'd have to keep acquiring the lock and releasing it, acquiring the lock and releasing it, because you can't check that variable unless you actually are the only one looking at it. I'm losing my train of thought here. Where'd I go? The problem with that, from a programmatic standpoint, and this is, I think, is a pretty good point, is that if you're basically while looping, you really aren't allowed to do anything meaningful until you get beyond the while loop. So what's going to happen is you're going to be hogging the processor. Maybe in the same time slice, you're going to just keep reacquiring and releasing the lock just to confirm that it's still 0. Does that make sense? That's what's called busy waiting. There are some scenarios where busy waiting is actually fine. It usually is in the case where you have multiple processors and you expect some other thread running on another processor to release a resource pretty quickly. But in a single processor environment, which is what we're pretending we have, there's no reason for a thread to spin lock and keep checking the value of a global variable because it's not going to change until somebody else gets it. Does that make sense? So this right here is this very clean way to say, you know what, I'm not making progress, let the thread manager pull me off, put me on the blocked queue. Only when someone signals the semaphore that I'm blocked on will the thread that's blocked on this thing ever be considered for the processor. The alternative is to use the global, exposed global with a binary lock, programmatically correct, but it encourages busy waiting, and busy waiting is like probably I don't want to say the worst thing. The worst thing is having a race condition exposed. But it's, as far as correct coding is concerned, it's the least good in terms of design because it wastes processor time. That could otherwise be shared to the people to the threads that really can get the work done. Okay, does that make sense? 2-second question, 4-minute answer. Okay, you guys are good with this right here? Okay. There's that. I want to start talking about a couple other things. I have 2 related examples. One I'll actually write code for, and then another one I'll just talk about the design. I want to start thinking about more practical problems. I'm going to frame the next example in terms of just FTP downloads. Okay, I know FTP is kind of this 1990s technology, but we all still use it. Okay, we actually go and fetch files. We actually use programs that use FTP. But let me just assume the existence of this function. I have this function, int. I'll call it download single file. And what I'll do is I will give it two things. I'll give it a const char star. I'll call it a server. And I'll give it a second name called path. I know you know what this means. Server is basically the computer that's hosting the file that you're trying to get. And path is basically relative to where the web directory or the FTP server is behind the scenes, how to get to the particular file of interest. Okay? So this is basically the computer it lives on, and this is effectively the file name with directory structures, nested directory structures funneling down and drilling down to where the file lives on the server. Okay? The return value here is the number of bytes that were downloaded to pull the entire file over. Does that make sense? Okay. What I want to do is I want to write this function called download all files. I want it to return the total number of bytes that were downloaded, as basically the sum of all of the sizes of the files that are downloaded. I'll call it download all files. I'm going to assume all the files are hosted on the same server. Okay, but I am going to give you char star files, an array of files in that server, and the number of files in that array. Now, 2 weeks ago, or a week ago for that matter, if I asked you to write this, certainly in an exam, you'd be dancing a jig because it's just a for loop, okay, with a plus equals going up and building up a return value. But in spite of the fact that it's the same computer, there are some problems with that. But just pretend that the server is capable of hosting as many simultaneous requests as possible. Okay? Does that make sense? What you'd rather do is you'd rather spawn off n different threads. Okay? Does that make sense? N threads where each one is dedicated to pulling over one of these files. Okay? Does that sit well with everybody? Okay. So I'm going to assume that run all threads has already been called, and this is running as part of some thread that was spawned in the main function. Okay? So I'm already dealing with a multi-threaded environment. What I could do is I could declare something called total bytes and set it equal to 0. And I can be prepared to return total bytes. You're not necessarily sure how that's updated yet, but you can be sure that each of the n threads I'm going to spawn off to download a single file is going to somehow do a plus equals against this thing right here. Okay, this is functioning somewhat as num tickets in the very first example, except we're adding to it instead of minusing from it. Okay. Now, thread new doesn't return anything. Okay. So what has to happen is that I have to spawn off n threads in addition to passing the server and one of the file names to the thread. Okay. So that the thread can call this function. I also want to pass the address of this integer right here. Okay. Does that make sense? And a lock that's designed to protect access to this, because you're going to have several threads trying to plus equals potentially at the same time. Okay? So I'm going to do this semaphore. I'll call it lock. It's equal to, I'm going to set it equal to 1. And that's this is just shorthand for what would really have to be there. And then I'm going to do this. For int I is equal to 0. I less than n, I plus plus. What I'm going to do is I'm going to call thread new. I don't care about the debug name, but I'm going to call this function called download helper. You may ask why I don't call this function directly. The function that's passed right here to thread new has to have a void return type. But even if it didn't have a void return type, there'd be no way to actually catch the return value from the thread new environment. Okay, so what really has to happen is I have to call this proxy function that sits in between this one and that one, that knows to call this one and also to accept its return value and do a plus equals against this thing right here. Okay, I have to pass in a few arguments. I have to pass in server. I have to pass in files of I. I should pass in address of total bytes. And I should pass in lock. That means I should pass in 4 parameters. Okay, and that's all I want. Now there is a problem with this. The setup already, but I'm just going to implement it like this is the okay thing to do. But conceptually, you know what's happening here. Basically, this thread is being the typical manager at a company where he doesn't want to do anything except delegate. Okay, and this thread has the responsibility of pulling all n of these files. It happens to have n employees or n people it can hire on an instant, like it just does right here. And it gives each one of them the task of downloading each of these things in succession. Does that make sense? This download helper has to be a function that returns void. I'll call it DH for download helper. And it takes these arguments: const car star server const car star path int asterisk let's say num bytes p for pointer, and then it has this semaphore I'll call lock. Now the semaphores, remember, are pointers themselves, so they don't have to. You don't have to pass the ampersand through. You can just pass lock itself. Okay. So you have a hook on the master copy of the integer that needs to be plus equaled against. What has to happen is that you want to do this int. Let's say bytes downloaded. And you want to declare that ahead of time, because what you want to do, actually I don't have to do that, I'm sorry. And you want to set it equal to the result of that function. Download single file, where you pass in server and you pass in path. It looks like it's being done sequentially, but it's not. There are n-1 of the threads trying to call this same exact function to download the files in parallel. Okay? Does that make sense? This is in the same spirit as the type of thing you have to do for assignment 6. Okay? The reason you kept the return value is because after you let this thing run and do its work, as a side effect of this function, you're just supposed to assume that some file in full appeared on your own host machine. But afterwards, what you want to do is you want to semaphore wait on the lock that all the other threads are quite possibly waiting on, because once you acquire that lock, you are the blessed thread that's allowed to plus equals against the single integer that you have a pointer to. So, num bytes p plus equals bytes download. Then you go ahead and you release the lock, and then you return. There's no explicit return value here. The thing that feels like a return value is actually a return value via reference via this pointer. You have the side effect of downloading the one file you're supposed to, and you're also supposed to update this variable to be that much higher, so that when the thing is returned, it returns presumably because all threads have returned and contributed to this thing. Okay, so when this happens, it really is the accumulation of all the bytes that have been downloaded. Okay, does that make sense? Okay. If I'm silly and I accidentally acquire the lock before I call download single file, it'll still run, but it'll be even slower than it would have been had you just not used threading at all and just done the download single files sequentially. Because this just means if I put this up there and this is serving as a binary lock, then you're putting the very important time-consuming function inside the critical region so that at most one thread can be involved in the downloading of a file. Does that make sense? So it's imperative that this be outside the critical region, and we only have one critical region, and it has to come after, since it has to appear somewhere, it has to come after you download the file. Okay? Does that make sense? Okay, now there's one problem with this right here. Do you have a question? I'm sorry, you have to say again?
If you had like 10,000 files to download, would it make all 10,000 threads at once?
Well, in principle, it would. That's a scalability issue that I'm not concerning myself with. I'm assuming that we're dealing with something like 40, okay, or even 100. Most thread systems, including our own, actually has a limit on the number of threads that can be reused. I'm sorry, that can be spawned off. Our system is like 500. Subsystems, it's like 1,000. And in principle, really sophisticated systems can actually reclaim threads that have completed and reuse that thread space for something that's created afresh. Okay, does that make sense? There is a little bit of problem with this. I frame this in a way that might not make sense to you, but I just want to make sure you understand it. Is that I'm assuming that run all threads has already been called, and this as a function is actually running in some other thread. And so what I really want this to happen is that this is a child thread of main to really be spawning grandchildren threads. Okay? If run all threads has already been called, and this is running, as soon as this is called, it actually sets this up, or all n of these up, on the ready queue immediately so that they start running immediately. Okay? I use the analogy on Monday, I think, of a dog that's already in the race giving birth to N dogs and throwing them back to the beginning of the race and letting them run. Okay? The problem here is that the way this is coded up, the job here is actually very easy. This is the equivalent of the manager at a company who's delegating all of his work basically going home before the work gets done. Do you understand what I mean? It's one thing for you to delegate work and then to go home for lunch and then never come back. It's another thing for you to delegate the work but then to wait for all of it to be done. Even if you're just in your office surfing the internet, you can actually you should hang out until all of the work is done so that you can properly return the total bytes value. Okay? The way this is technically coded up at the moment, it says, okay, I'm going to declare a local variable. I'm going to, I'm going to share a lock with all of my underlings over here, so that they all have atomic synchronized access to the shared global right here. And I spawn them off, and then I return immediately. It's quite possible that I would return a 0 here, because I may advance from the very last iteration of the for loop to this return statement. Okay? Does that make sense? Before any one of these threads makes any partial progress whatsoever. Presumably, this is a time-consuming function, like on the order of like milliseconds or even seconds. It would take microseconds. It would take milliseconds for it to advance from the very last thread to this one right here. Okay, it's quite possible that maybe in 1 or 2 time slices, all of these threads could be spawned off, and it could return before that makes any work whatsoever. So what really has to happen is right there. I really need the manager thread, the download all files thread, to really block and not go anywhere, and certainly not advance to the return statement until it has verification that all of these guys have completed. Because if they've completed, then the manager knows that this thing has really been built up to have the true return value. Does that make sense to people? Yes, no? Okay. So what do? Well, not surprisingly, you use concurrency and you use semaphores to basically implant thread communication, thread-to-thread communication. The reader-writer example, we have the reader and the writer communicating in this binary rendezvous way. When I do this, I'm talking about the crisscross of semaphore signal and semaphore wait calls, so that each one could tell the other one that there was an empty buffer or a full buffer. Okay? There was this one-to-one relationship between reader and writer there. I really have a one-to-n relationship with this setup. I have a single master thread right here that's supposed to do all the work. It elected to spawn off n threads to get the jobs done because it can take advantage of parallel computing right here, okay, and download many of the files simultaneously. What really has to happen is I need about 6 inches more of board space. What I want to do is I want to declare a semaphore up here, and I'll say children done. And I'm going to set it equal to 0. I'll do the same thing there just to make that it really is a semaphore new call. What I want to do is I want to use this children done semaphore basically as this connection to each of the threads that it's spawning off. I wanted to do this for int I is equal to 0, I less than n, I plus plus. I wanted to semaphore wait on children done. Now I haven't passed children done to that thing yet, but I will in a second. What I want to do instead is to change this to a 5. I want to pass down children done as an extra parameter. I have to abbreviate because I'm out of room there. Okay? So what I'm basically doing is I'm giving it's almost like a little baby monitor to each of the threads, okay, that I'm spawning off. And when each one of them's done, they go wah into the baby monitor in the form of a semaphore signal. And when I hear n of those, okay, I know that all of the threads have completed. Does that make sense to people? So the signature for this has to move over a little bit. Semaphore, I'll give it a different name here. I'll call it parent to signal. And then before I return over here, I will semaphore signal the parent to signal. This is the wah into the baby monitor. And this thing is actually aggressively for looping, okay? And its semaphore waits on this thing not once, but n times. Once for each of the threads it spawned off. Programmatically, each thread signals this thing exactly one time. So I expect this thing to be signaled exactly n times. I need all n of those signals in order for this thread to know that it's done. Does that sit well with everybody? And then once I have that, I can advance to the return statement, knowing that it's safe to return total bytes there because all of the n threads I gave birth to have actually done their work and died. But as a side effect, their legacy was to plus equals my total bytes integer. Okay? Yep?
Is there any way that there's a way, it seems like there's a way to increase the number in semaphore? Is there a way to decrease it?
Well, semaphore weight certainly does decrease it. If this is surrounding a 7, semaphore weight brings it to a 6. Okay, that's so semaphore weight is like a minus minus that's guaranteed to be atomic, and it's also a block if the number inside happens to be 0. Semaphore signal is an atomic plus plus and not much more than that. Okay.
You could initiate it to n the semaphore children. Have not done, I guess, and then increase the other one until the lock is
right. But I have our version of the semaphore. Some more recent libraries have decided to do this, even though there's an argument against it. You'll notice, and this is mentioned in the handout, we don't provide a get value within method on the semaphore. We could ask for the value of the semaphore, okay? And we could say, oh, what is the value now? And it tells you 7. And you go, oh, I'm going to act on that 7, right? But it may have changed by the time you get a chance to act on it, because in theory, if you have a lot of threads, the time between the return of get value within and the code that acts on that value could be separated by seconds. Okay, exaggerate it. Think about it in terms of years, which is what it really effectively feels like at the processor level. Okay, a lot can happen in years. Okay, so you don't necessarily, you can't trust a value that was acquired from within the semaphore and act on it until you've actually released a lock on the check. Okay, does that make sense? Now, actually getting a 0, there are some situations where it would be okay. You could keep on looping and only break out once you get the value out. That's a 0. But that's a busy waiting thing that I was arguing against when I answered a question earlier. Does that make sense? Technically, this is a little bit of busy waiting, but it makes as much progress as is possible until it blocks because not enough children threads have completed. There are some versions of semaphores. The one I'm thinking about are the ones that come with the 1.5 version and later of Java, which you'll learn all about in the autumn when you take 108. Do you notice that semaphore wait right here, it's an implicit request to just do a minus minus, a minus equals 1, right? There are some flavors, not in our library, but some more modern libraries, where you can actually wait for a total of like n, or 12, or 20, or 3 dozen, or whatever decrements against the semaphore, and just call this once as opposed to exposing the for loop. There's an internal for loop instead. Does that make sense? Okay. Ours, it's exposed. I actually think that's fine at this stage of the game because I want you to understand the mechanics of what's involved in order for this thread to block. Okay, and it's not technically busy waiting, so it's not really a bad design. Okay, make sense? Okay, question?
Yeah, there is nothing to prevent all the threads from downloading the same portion of the file.
Well, I didn't. Not the same portion of the file. My assumption is that each of these files is actually different, and I'm just assuming. I didn't mention it explicitly, but I'm assuming that download single file is this thread safe function that doesn't actually interact with other calls of the same function at the same time. Okay, which is technically not true because two download single files may have to create the same directory on the host machine, and that would be a little bit problematic. Except that the make directory command is implicitly atomic on the operating system anyway. I'm sure it is. I've never read that, but I'm sure it is. Okay, you get the setup here? Yep.
Is there any reason not to initialize children to n and you decrement it there and just semaphore wait once at the end?
But the thing is, if you semaphore wait, you might wait on it. You want it to semaphore wait after it's become 0. There's no way to do that. Like semaphore wait will succeed if it's positive, and you're making it initially positive. All you're going to do is make it n plus 1, okay, or take it from 0 to 1 at the end. But it's like you actually want it to. The only way you can block if it's semaphore waiting on a value of 0, and you really do want this thing to halt. Okay, does that make sense? Okay. Some versions of the library, and actually we can't initialize, even though a semaphore in our world can never go from 0 to a negative number, some versions, the Java library does this as well, allows you to initialize a semaphore with a negative number. Okay, that seems a little weird, but if I were to initialize this semaphore to be negative n plus 1, and then I had a single semaphore wait call here, it would have to be signaled n times before it became positive. Does that make sense? So that's what I think the two of you are trying to get at. It's just not supported by our version of the library, or our particular thread library. Yep?
So in the helper function, could you have eliminated one of the semaphores, like made pass them and have an array of counters and sum all the counters at the end?
I'm sorry, what? Oh, I see what you're saying. So in other words, you're thinking like somehow do
let's say you're an array of integers and each helper guy gets a reference to one of the elements of the array, so you don't really need to have a global counter.
I'm not quite understanding. I think I know what you're saying. Are you just asking this thing to pull like an array of Booleans or something like that?
Let's say you get total bytes into an array.
Into an array, yeah.
Of 10 elements.
Right.
Each.
I see what you're saying, yes. I have seen that before. What he's suggesting, I think, it's pretty clever, although I think it's clever, but I think it's just a little bit more work than it needs to be. He's setting aside not just one integer, but an array of length n, where each of these things can write without fear of race conditions to a slot in the array that's dedicated to that thread. And then once you get past this point, you'd still need the children's done semaphore. You can go through and safely do all the addition yourself there, right? That's actually a fine idea. And actually, I can't even say that it's a bad thing. In many ways, it's actually pretty good. The only thing about it that might be problematic is that, I mean, the number n here is huge. But even that's not that big of a deal. So it's a great idea. Yep.
Referencing back to the question 2 questions ago, if you made children done equal to n,
Right.
And you replace the for loop with a while children done does not equal 0,
Right.
would it work then? And just
Well-
have like a closed while loop?
Well, you can't do equals 0 on child's done. I'm writing this as shorthand, but it's not really an exposed integer. This one doesn't actually, if the semaphore did provide a get value of method or function, there are a lot of scenarios where that type of functionality breaks down, but this would be one where it would work because it's only going to hit 0 once. So that is true, but it's interesting to explore that if you want. Like after you've done this assignment 6, you should go. You already know enough Java to digest the syntax. Just go and read like the 2 or 3 pages of the concurrency model in Java 1.5. You're going to read it anyway if you take 108 rather in the autumn. just so you understand all the things that are available in more sophisticated thread libraries. Okay, I just wanted to minimalize. I wanted to. Basically, we've used this package for so long because it really is lean and clean and very easy to digest in full. So you have to do all the interesting things in terms of the atomics. Okay. You guys doing okay? Okay. I do want to make it clear that when I initialize this to 0, I may get down here and I may spawn all of these things off and in theory semaphore wait against a 0 and block immediately. Does that make sense? I may actually get swapped off right after this closed curly brace, but not get inside the for loop immediately. I could get swapped with the processor as this download all files thread. It might be the case that 50% of these things actually complete and promote this from, say, 0 to 6 because there were 12 child threads. Okay? And this thing would come down right here, and it would happen to notice, or not notice, but it would benefit from the fact that this thing had been promoted 6 times, so it would make 6 immediate for loop iterations, or carry through all the six of the iterations immediately before it's blocked on the 7th. It's not a problem. Okay? It's technically possible for the download all files thread to exit before the download helper thread does. I'm sorry, before any of the 12 download helper threads exit. Now you would think that'd be a problem, but this is the scenario. This one blocks the 12 different threads that I spawned off. All get this far and they get swapped off just after they return from semaphore signal here, but before they actually call the return instruction to emulate the closing curly brace. Do you understand what I mean when I say that? So all 12 threads could, like, right before here be swapped off a processor. And this thing could get the time slice after that's happened, get the processor back and say, oh, wow, look, I actually went through this thing 12 times, and I can return an I do. Okay? You're not, I mean, if you want to be as completely realistic about the simulation as possible, you can do it. But you have to effectively understand that this function is really over when SS, semaphore signal, returns. And that to the extent that you needed the information to flow and be synchronized the way it is, it still works. Okay? Does that make sense? In Java, you actually have the option of releasing the lock after the closed curly brace. There's a keyword in that language that doesn't exist in C and C++ called synchronize. You'll become very familiar with it next autumn. That releases the lock after you formally finish the method, and I say formally finished, after you've gone past the closed curly brace. Okay? But I don't care in this situation because all I really used the semaphores for was to get a meaningful full total bytes value. Make sense? Okay. So there's that. I have 5. Oh, go ahead.
Right, that blocks the for loop, nothing else, right?
This one right here, yeah. This it's a one-line body of the for loop. So just this is right here, and like that. Is that what you're asking? Okay. Very good. Okay, so what I want to do is I want to set up a big example for Monday. Okay. All of the examples have been focused primarily on either 1 or maybe 2 synchronization directives. The handout I gave out today has this great first 2 or 3 pages that was written 10 years ago, but it hasn't changed. It hasn't changed in 50 years, really, much less the last 10 years. It describes all of the different patterns that you have to be sensitive to, or situations you have to be sensitive to, and the patterns you use to be sensitive to, to actually make sure that you don't have race conditions and you avoid deadlock. It's all about protecting global variables in a binary lock or a critical region situation, and implanting directives for 2 threads to communicate with one another, 2 or more threads to communicate with one another. Okay, so it's good stuff to read. I've hit on all of it in the past 3 days, or past 3 lectures rather. The large example in this handout, it's a little intimidating. It's actually larger than any exam problem. It's probably the merging of 2 past final exam questions from like 10 years ago. It's a great problem. Okay, it is the ice cream store simulation, and all I'll do is I'll set it up so that you know what all the players will be in this big, grandiose ice cream store. Okay. We're going to have 10 customers. Okay? There's going to be a customer function. We're going to spawn off 10 of those things. And we're going to actually know how many ice cream cones each of the customers order. It's going to be between 1 and 4. Okay? There's going to be a cashier that each of the 10 customers approaches as they're ready to pay. So there's a little bit of contention, and I think there's already clearly a flavor of concurrency and race condition going on, because these 10 customers have to approach this cashier, and the best metaphor I can think of is when your mom, when you were going with her little kid to the market, she'd have to go to the deli and she'd have to potentially edge out and get atomic access to that little number thing. So you pulled the 33 or the 94 or whatever it was, and you always looked at the number, it was like 22 away, and you go, oh my God, we're going to be here forever. Okay? But there certainly is going to be thread-to-thread communication between all the customers, okay, and this one cashier. Make sense? There's going to be a single manager thread. I'm being very cynical about managers, but this manager doesn't do very much either. What he does is he approves or disapproves of ice cream cones. Okay, he doesn't make them himself. He just approves and disapproves of them with like a coin flip is what really happens. They're going to be between 10 and 40 clerks. The reason it's 10 and 40 is because every single customer is going to give birth to a clerk thread, one clerk for every single ice cream cone that needs to be made. So the people who are ordering, they're really impatient. This is real life. If they have 4 ice cream cones to be made, they want all 4 to be made in parallel. Okay. So the customer never sees the manager, but these 10 customers interact with 10 to 40 clerks, order the ice cream cones, they accept the money, make the ice cream cones. All the clerks interact with the manager. They have to acquire a lock on the manager's time, okay, because the manager is overwhelmed if more than 2 people are in his office at any one moment. So we can only accept 1 person in the office with 1 ice cream cone, so there's no confusion as to which ice cream cone he's approving or disapproving of. Okay, does that make sense? So we're going to run a simulation where there are up to 52 threads running simultaneously, and there's certainly going to be 4 different types of threads. Okay, I want the manager to basically arrive at the store and not to leave the store until he's approved the number of ice cream cones that he needs to approve. I want each thread, the clerk, to only to live as long as it's necessary to make a good ice cream cone and hand it over to the customer. I want the customers to be able to order their ice cream cone, get it, go and pay for it, and leave the store. I want the cashier to know that he's rung up 10 different customers. Does that make sense? Okay. So to the extent that you can read the problem statement between now and Monday, that's great, although don't worry if you can't, because I'll certainly review this beginning of Monday. But even though parts of the simulation are certainly a little contrived, they're contrived specifically to bring out some scenario where you have to deal with concurrency properly, okay, and use semaphores to either foster thread communication or to manage binary lock or access to a resource. Okay? So have a great weekend. I will see you next week. Hey.
Oh, so